Good afternoon, students. Today I'm going to start with a new chapter, that is D and F block elements. Okay, this is a very important chapter as I told you. So D and F block elements. So listen, students. In this D and F block elements, this chapter covers 8 marks. Okay, so that is 2 marks, one question, that is question number 14. Okay, 3 marks, 2 questions. This question number 23 and question number 24. Question number 23 and question number 24. So this chapter covers 8 marks, students. In that, one 3 marks question is specially from the preparation of the compounds of some important D block elements, that is potassium dichromate is there, potassium permanganate is there. So this is the main, I told you, this is the 8 marks chapters. Okay, so here 2 marks, one question is there, that is question number 14, and 3 marks, one question is there. 2 questions are there, that is question number 23 and question number 24. In that, question number 23 is always preparation of K2Cr2O7 and KMnO4. This may vary. Okay, this is depends upon the properties of either these elements or the properties of the D block elements. Okay, periodic trends. So this is the chapter discussion. So what are the objectives in this chapter? So what we are going to study in this chapter is, so first thing is electronic configuration. Electronic configuration. So electronic configuration, the position in the periodic table also we will study, but I'll explain. Main thing is electronic configuration. Next, the periodic trend, especially the properties of the D block elements, how it changes. Okay, in that second one we are going to study is physical properties. Physical properties. Next, periodic properties. Next, periodic properties. That may be oxidation state, ionization energy, electron gain enthalpy, atomic radius, ionic radius, metallic radius, whether they are paired, unpaired, magnetic, everything. That is periodic properties we will study. Next, fourth one is some important compounds of D block element, especially K2Cr2O7 and KMnO4. Especially K2Cr2O7 and KMnO4. Next, fifth one, chemical properties of these two, K2Cr2O7 and KMnO4. Next, F block elements. F block elements. Okay, last one is, that is 7, uses of D block and F block elements. Just you remember uses. Okay, so these are all the objectives we are going to study in this chapter. Electronic configuration of D and F block element, physical properties, periodic properties, some important compounds of D block elements, especially K2Cr2O7 and KMnO4, these chemical properties, F block elements and their uses. Okay, so students, in this first I will discuss completely about only D block elements. Later in the F block element, I will explain again the configuration of F block elements and why they are called and like inner transition. Okay, why they are called as lanthanides, why they are called as actinides, I will explain while I am studying, while I am explaining the D block element. So F block element. Okay. First we will go with the D and D block specialty. Okay. So listen, why the elements are called as D block elements. So for example, you know, it is a periodic table means here two S blocks are there, correct? Here P block is there. This is noble gas. 1, 2, 4, 5, 6. Correct? So next series are there. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Here again, this is the periodic table, and here F black is there. Okay, students. Here this is the typical representation of what the periodic table. This is S black, this is P black, D black, and F black. Okay. So listen, I think now writing exactly in the first year we studied S block and P block elements, correct? So in S block elements we consider them along period. Sorry, group means hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Like that. So here also beryllium, magnesium, calcium, barium, strontium. Okay, so beryllium, magnesium, calcium, strontium, barium, radium. Like that. Here also we consider group. But these D block elements are studied along period, not group, because they show same properties and there is not much difference between one element of one group and the other element of the next group. So, but in series they show different variations. That's why these D and F block elements are studied as 3D series, 4D series, 5D series and 6D series. And this F is like 4F series and 5F series. So these D and F block elements are studied in series, not in groups. The reason is they show variation in their properties along period but not group. Why they didn't show the variation in group? I'll explain why I'm telling them what is the difference between SPG and F block elements. Okay. So listen, the elements, this group is start from 3rd and ends at 12. Okay, the elements which are present are the starts from 3rd group to 12th group. Okay, along or vertical means 12th, 3rd group to 12th group. So total 10 columns are there. So in the elements present in that 10 column is called as what? D block elements. So why they are called as D block elements means the last electron, if we write the configuration, the last electron enters into the D subshell. Okay, if we keep on writing, for example, chromium is there, atomic number 24. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So this last electron enters into D subshell, hence this is kept under D block element. Okay, sodium is there, its atomic number is 11. Okay, configuration 1s2, 2s2, 2p6, 3s1. Your last electron enters into the first S subshell, so that belongs to S block. This is the way how we classified SPGF block. Okay, so here the D block elements means the last valence electron which enters into the D subshell. Those are called as what? D block elements. So the general electronic configuration of D block elements, especially, okay, that is noble gas. NS1, NS2 or 1 to 2 it may be, not exactly 2, 1 to 2, N minus 1D, 1 to 10. Why I wrote 1 to 2? I'll explain later, students. So noble gas NS 1 to 2, N minus 1D, 1 to 2. Why listen? NS means this, N minus 1 means this. If d orbital is there, must ensure that s orbital as, so this will fill up first according to n plus L rule. I know why 4s fill first. Then 3D means it has n plus L value less compared to this, because n value means principal quantum number, L value means azimuthal quantum number. If we add both, we will get the greater number, that is higher energy. If we get a least value, then that is the lower energy. The n plus L value for 4s is less, 3D is more. That's why 4s orbital fill up takes place first. Okay, because we know the electrons, filling up of electrons takes place in the increasing order of the energy of the atomic orbitals. Okay, so this is all about the general electronic configuration. Here this is the outermost electronic configuration. Outermost means valence electronic configuration, 1 to 10 ns, 1 to 2. Almost that is ns2. For only 2 cases, for chromium and copper, this is varies as ns1. For except for copper and chromium, all are ns2 configuration only. Okay, so this is all about the period, the position of the d block element in the periodic table. So listen, these d block elements are also called as transition elements. Correct? D block elements are also called as transition elements. Why they called so means, so they are placed in between S and P block. As I wrote before, they are placed in between S block and P block elements. They are transist between both S and P block, because in that metals are also there, non-metals are also there. Not that much. They show the properties in between S block and a P block orbital. Okay, so P block elements. That's why they are called as what? Transition elements. Only that means the name transition. Only the thing they placed in between S and P block elements. Okay, so we are going with the electronic configuration, students. As I told, first properties, electronic configuration. Okay, you know, along the group all the elements show same type of configuration means I'll consider only one series, that is 3D series. So 3D series of this d and f block elements starts from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. I think you may see. Okay, scandium, titanium, vanadium. Guys, I'm going to here. Titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, students. So total 10. I told this is third group, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12. Okay, the D block element starts from the group 3 and ends with the group 12. Okay, total 10 elements are there. That's why I told you, while we are writing S orbital, we consider only 2 electrons. While we are writing P, we consider 6. While we are writing T, we consider 10. While we are writing F, we consider 14, because as the atomic number increases, then the number of electrons in the orbitals also increases. So listen, in the d orbital total 10 columns are there. So here 3, 4, 5, 6, 7, assume that is the atomic number, then the 10 electron has the capacity to fill up in the d block. Okay, that's why this is a number of electrons. In s orbital only 2 blocks are there, 2 electrons. In p orbital 6 blocks are there, 6 electrons. In d 14 groups are there, that's why it is d10. In f 14 groups are there, and so it is f14. Okay, so listen, as I told you, the configuration is noble gas n-1d 1 to 10 ns 1 to 2. Okay, so students, I didn't consider noble gas here. Otherwise, I write what is the noble gas present here is argon. That is atomic number 18. Okay, so the atomic number, I'll write later. So atomic number scandium is 21, yeah, 22, 23, 24, 25, 26, 27, 28, 29 and 30. Okay. Next, if you want to write the configuration, noble gas is there. Okay, that is all the case. Argon. The same thing follows here. Next, Ns 1 to 2 is there. Next, Nv 1 to 10 is there. First, I will write S orbital. So, listen, 18 are there. 21 electron is here. This is argon means 18, that is noble gas configuration. 21 minus 18 means 3 electrons there. So, Ns2 3d1. So, this is Ns2 d2. Okay. I consider that. Okay, this is correct. I'll write it here. Next, Ns2 d3. Next, this is Ns1 3d5. Okay. Next, here 2, here 5, here 2, 6, 2, 7, 2, 8, 1, 10, 2, 10. So this is the electronic configuration, students. So while we write these things, we will get finally noble gas, that is argon 3s2, argon 4s2, 3d1 for this. Okay, here 4s2, 3d2, here 4s2, 3d3, here 4s1, 3d5. Okay, here 4s1, sorry, 4s2, 3d5, here 4s2, 3d6, here 4s2, 3d7, 4s2, 3d8, 4s1, 3d10 and 4s2, 3d10. So this is the electronic configuration of the first group series. Right? The first series, that is 3D series. That's why it takes 3D, 3D, 3D. If next is there after scandium, that zirconium is there. Sorry, not zirconium. After scandium, ytterbium is there. Okay, so this thing next ytterbium series follows what? 4D, 5D, 6D. Sorry, 4D1, 4D2, 4D3, 4D5 like that. But the electronic configuration follows the same thing. This is the way students. Okay, what happens here is, so listen here, 4s2 is there, 3d1 is there. Of course, the valence electron enters into a d section. d1, d2, d3. Here d4 we expect d5, d6, d7, d8, d9, d9 and d10. But instead, here only in the two cases we have the configuration d5, 4s1, 3d5 and 4s1, 3d10 instead of 4s2, 3d4 and 4s2, 3d9. Why? Because compared to s orbital, listen, this is s orbital, this is d orbital. Okay, if we wrote 4s2, 3d4 means this is unstable. Correct? By removing one electron and placing one electron here, the rearrangement itself takes place. Then what happens? This also become off-filled, this also become off-filled. So compared to completely filled configuration, the off-filled configurations are very stable. So here also same thing, here also same. Okay. So because of that reason, chromium and copper shows the off-filled configuration 4s1, 3d5 and 4s1, 3d. Okay, so students, as I told, this Ns subshells, what Ns, here I write, Ns and Np subshells are called as valence shells. and N minus 1d subshell is penultimate shell. Okay, this is penultimate shell. Okay, so the last electron which enters into the penultimate shell, that is called as what? D block element. Okay, students. So this is all about the electronic configuration. Here only the one difference you have to remember the electronic configuration of chromium and copper. Okay. Next, physical properties. In that physical properties, melting point is there, boiling point is there, refractive index is there, arrangement of the atoms are there, okay, metallic nature is there. Okay, so second one is periodic, not periodic, physical properties. Okay, students, in this physical properties, the main thing we are going to discuss is, so listen, physical properties, these are all called as metals. Almost all the D block elements are called as metals only. They show malleability, ductility, melting point, boiling point, conductivity, everything remains same. But while we consider the melting point, that depends upon the what? Metallic bond between the atoms. Okay, so students, if we assume, or I'll write diagram here first. So this is atomic number, this is melting point in 10 to the power 3 kilojoules. Okay, so here what happens? The trend, so this is, assume this one is 1, this is 2, 3 and 4. Okay, so then what happens? This increases, again decreases, here it then decreases. Okay, this is the, so students, this is Mn, Cr, vanadium, titanium, next this is copper and zinc. So this iron, cobalt, nickel, copper, zinc. The way that is decreases. Why? I'll say, students. So listen, what is metallic bond? How the metallic bond takes place means, I'll write one example. Scandium doesn't show any metallic bond here. So I will start with the titanium. So it has configuration 3d2 4s2. Okay, we will consider this is completely filled configuration means we won't consider 4s2 shell, we consider only 3d. So listen, student, as we move, so D block element, here titanium is there. Okay, so for titanium 3d2 configuration. Correct? So next, here we have 3 vacant orbitals. So we have 2 unpaired electrons. These unpaired electrons have the capacity to bond it with other titanium atom to form, it gets paired up, so it forms a metallic bond. So here unpaired electrons are there. This is d orbital of titanium. Correct? So you see, this is another d orbital of titanium. They get share electron between themselves. Then the metallic bond takes place. Okay. So next, another one is vanadium. Configuration is 3d3. This is 3d2. Here what happens? 1, 2, 3. Number of unpaired electron increases, means the bond increases, thus results in greater the metallic bond. Number of unpaired electron increases means the intensity of the bond formation and the ability of the bond formation increases. Next, for 3d4, that is chromium, 4 electrons are there. Here it is also having high metallic bond formation capacity. So listen, here for chromium high is there, for manganese it is decreases. Why so? Listen, if it is 3d5 4s2 is the manganese configuration. If we have write the box diagram, we get electron in the each orbital of the d block. So it has half-filled configuration in the all the orbitals. Half-filled configuration is quite stable compared to this incompletely filled configuration. So this is highly stable means it never easily make bond with the any other atom. So that's why the metallic bond in manganese is weak. Why it is weak? Because it has a half-filled configuration. Half-filled configuration is stable, so it won't able to break that, or it don't want to like to break that stability of that orbitals. That's why it never form a metallic bond. Not never form, it will form, but the bond is very weak. That's why here the melting point decreases. Okay, this is the graph. After chromium increases due to increasing unpaired electrons. For manganese it is decreases even though unpaired electrons are more. Why? Because it attains a stable configuration, that is half-filled configuration. Again for iron, cobalt, nickel, copper, it completely decreases, students. Why means I'll show here. So this is up to what? Manganese. Okay, I write here. For iron, it is 3d6 configuration. That means 1, 2, 3, 4, 5 means 1, 2, 3, 4, 5, 6. Okay, here one paired electron is there. Only 4 electrons we have unpaired. Okay, so then the metallic bond number of unpaired electron decreases here, and the stability also not. This is that much not stable than this manganese. Hence, again the melting point increases. Okay, so you keep on moving, that is 3d7, 3d8, 3d9 and 3d10. This gets paired up. If pair up continuously takes place, this is for 3d7 means 1, 2, 3, 4, 5, 6, 7. Unpaired electrons is only 3. Again the metallic bond making ability decreases. Again here pair up, only 2 unpaired electron, pair up. So inside it has very less melting point, students, because it has completely filled configuration that is almost equal to this. So chromium and zinc, manganese and zinc shows least melting point because of the stable electronic configuration. So this is the trend follows in the series. Period. Okay, in 3D series, after chromium increases because of the increase in the unpaired electron, for manganese decreases because of the stable configuration, after stable configuration, up to copper remains, again up to zinc decreases because of the pair up of the electrons takes place. So why I am explaining these things, students? I told you in a 14th question number 14, 2 marks question tell us that maybe depend on this. Why the melting point of manganese is less? Why the melting point of zinc is less compared to all the other elements of the D block element? So here what happens? The electronic configuration matters. Okay. So this is the melting point. Next, another one thing, students. So how the melting point means? By breaking the bond between them. Okay. If the number of electron increases, to break the bond, we need to break the force of attraction between the electrons. If the number of electrons increases means the atomization, the energy of atomization increases. We have to divide them into the respective atoms means we require more energy. So more energy we require means what happens? It is less stable. Okay. So this is the physical properties of what? D block elements. So the next one is atomic and ionic radius. So listen, students, as we know, the atomic and ionic radius decreases along the period and increases along the group. This is atomic number, this is atomic radius. This is atomic number, this one is atomic radius. I'll take three series here, 3D, 4D and 5D. Okay, so listen, this is 3D series, this is 4D and this is 5D as well. So 3D series keep on decreases the size as the atomic number increases. Assume this is scandium, our atomic number increases in the word D1, D2, D3, D4, D5, D6 up to D10. Okay, next, this is 4D series, means it also decreases in the same manner. Okay, if we come to 5D series, students, it's small, that much different. This is only a very small difference, 5D. Okay, so here what happens? It is in this form. Okay, so listen, 4D series and 5D series shows somewhat same type of atomic and ionic radius. Why it is like that? So listen, I told you 4 types of series are there: 3D series, 4D series, 5D series and 6D series, students. So here what happened to the atomic radius along the period is, of course, as in the periodic trend, along the period the atomic and ionic size decreases. But here what happens? This d block element shows variable oxidation state. For example, Mn, that is manganese, is there. It shows oxidation state of +2, +3, +4, +5, +6 and +7. Okay, so the size of Mn in +2 oxidation state is high, in +7 oxidation state is low. As the positive charge increases, size of the ion decreases. That we know. Okay, so these d block element shows variable oxidation state, so we can't say the ionic and atomic radius change properly. But if we consider any one fixed oxidation state of the d block elements, means from scandium to zinc, all are in +2 oxidation state, then the periodic trend follows the same thing. Along the period, the size of the atomic size or ionic size of the elements decreases. Okay, because of addition of extra electron to the d subshell, increase in the effective nuclear charge results in the decrease in size. Okay, so next, students, as we come to group, of course, in 3D and 4D, 4D series has greater size compared to 3D series. Along the group, size must be increases. So 4D series has the greater size than 3D series. But what happens to 5D and 4D? As I told here, students, 5D and 4D series shows almost similar size. Almost. So why? Because listen, this 4D series and 5D series are approximately equal. Approximately equal. Why both the series are approximately equal means, so listen, after this 3D, 4D, here lanthanides and actinides will come. Lanthanides and actinides will come. So as I told you, students, so NS subshell means if S orbital is there, if it is NS subshell, D are NS and NP are the valence shell. N minus 1D is the inner orbital shell and N minus 2 F is the again interior shell. So then what happens? Here nucleus is there means, so n minus 2 subshells comes first. Next n minus 1 d subshell. Next ns and np shells. Okay, if this is the nucleus, n minus 2 comes first, next n minus 1, ns and np. So here what happens, if the number of electrons entering into this SF subshell increases means that result in the increasing effective nuclear charge, the core shielding effect. So because they never repulse the incoming electron of d and sp orbital to electrons to the d orbital and the s orbital, and they never repulse the incoming electrons because of the core shielding effect. Okay, so the structure, you know, the structure of f orbital is so complex we can't easily distinguish the shape of the orbitals. Like, you know, for s orbital spherical is there, for d orbital double is there, for p orbital double is there. Like that, we can't say the proper shape of the orbital for f block element. So then what happens, due to that or any other reason, this shows a very poor shielding effect. Shielding effect means the opposition caused by these electrons to the incoming electrons. So the poor less shielding effect means resulting in increasing effective nuclear charge that results in the size. So due to the presence for involvement of F block elements here, the 4D and 5D series shows same type of or the same size, similar size, that is called as what? Lanthanoid contraction. This is very important. While I am explaining the F block elements, I will again say what is lanthanoid contraction, what is its causes, what is its consequences. Okay, so this is 3D, 4D, 5D and 6D series. So 4D series, of course, the size of 4D series is comparatively and appreciably greater than 3D series. They follows the trend, but in 4D and 5D they show similar size because of the involvement of F block elements leads to lanthanoid contraction. Okay, so this is the trend. So this is all about, students, the atomic and ionic radius. So ionic radius, as I told, these d block element shows variable oxidation state. Why the oxidation state? Because it has number of 100 electrons in d block, valence electrons. So many electrons from s subshell as well as d subshell. So each they have the capacity to lose each electrons, means they show what? Different atomical, different atomical ionic radius. Okay. So ionic radius means, as I told, manganese shows more than 7 oxidation states. Sorry, 2, 3, 4, 5, 6, 7. Okay. It shows 6 oxidation states means the ionization energy, not ionization energy, the ionic radius decreases. For example, I told you M plus 2 ion has greater size than M plus 3, than M plus 4, then Mn, manganese I'm telling, then Mn plus 5, then Mn plus 6 and greater than Mn plus 7. So the ion with the maximum cationic charge or a positive charge has least energy. So more positive charge, less size. Okay, more or less positive charge. Less positive charge, because these are metal means they show only positive oxidation state, not negative. So less positive charge means more size. So in this Mn, Mn plus 2 is the least charge and plus 7 is the largest charge, means this is smaller in size, this is greater in size. Okay. So students, this is all about the atomic and ionic radius of the D and F block element, D block elements, the trend follows. Okay. So in the tomorrow's class, I am going to tell you about all the remaining periodic properties of the elements, especially D block elements. So for you students, one question is there. That is very, very important. Often they used to ask in the examination why zirconium and osmium shows same atomic and ionic size. Give reason. Okay, this is very, very important for 2 marks. Okay, for this student you have to answer and you send answer to me in the group. Okay, thank you.